Hello students, welcome to this section, the L infinity spaces. So in order to define the L infinity space, in previous class we already defined the space capital LP. What is capital LP? Capital LP of E equal to set of all functions, set of all measurable functions f such that integral over E mod f raised to p is finite. That means it is p integrable functions. So in a similar way we can define the L infinity space. So for that, let E be a measurable set. E be a measurable subset of real numbers, and script f be the collection of all measurable extended real functions on E which are finite almost everywhere on E. Okay, then if you define tilde is a relation on script f such that f is related to g if and only if f is equivalent to g. Okay, then this relation is equivalence relation. It will partition the whole set script f as an disjoint union of equivalence classes. Then we proved that equivalent classes are denoted by f restricted to equivalence, which is a linear space over R. We proved that in the previous class it is a linear space over R. Okay, then in order to define the L infinity space, that means actually LP space with the p equal to infinity, right? P equal to infinity. For that we need a definition. Okay, so a function f belongs to script f, that means measurable functions, is said to be essentially bounded if there exists some m greater than 0 such that real number m greater than 0 such that modulus of fx is less than or equal to m almost everywhere on E. So a function is said to be essentially bounded. Note the term essentially bounded, not the boundedness, which is slightly different from boundedness, which says that if there is a m such that modulus of f of x is less than or equal to m almost everywhere on E. That means if you consider the set of all x such that modulus of f of x is greater than m, that means the unboundedness points, then that measure will be 0. This function bounded almost everywhere on E is essentially bounded meaning. A function is said to be essentially bounded means it is bounded with almost everywhere on E. That means if you consider the points at which f is unbounded means mod f of x greater than m avunna x galude collection eduthu kayinal the measure of that set will be equal to 0, which is the meaning of a mod f of x less than or equal to m almost everywhere on E. Okay, this kind of functions are called essentially bounded functions, and that bound m is called essential upper bound, and this m is called essential upper bound. Okay, so if there exists a m satisfies this property, that function is called essentially bounded, that m is called essential upper bound. Then a function may have more than one essential upper bound. So we define what is essential supremum of that function. So essential supremum of an essentially bounded function. Essentially bounded function is nothing but infimum of set of all m such that modulus of f of x less than or equal to m almost everywhere on E. So you consider all the essential upper bound, then you take the infimum of that ones. So that will be called essential supremum, or which is nothing but least essential upper bound, right? എല്ലാ essential boundകളിലും ഏറ്റവും ഇൻഫിമം എടുക്കുക പറഞ്ഞാൽ that will be least, right? That is least essential upper bound is called a essential supremum. Essential supremum of F. Okay. Now we define what is L infinity. L infinity of E is nothing but the set of all equivalent classes F for which F is essentially bounded. That means set of all measurable functions which are essentially bounded. Essentially bounded ആയിട്ടുള്ള measurable functionsന്റെ കളക്ഷനെയാണ് നമ്മൾ L infinity of E എന്ന് റെപ്രസെൻറ്റ് ചെയ്യുന്നത്. Okay, and we can prove that it is also a linear space, actually which is a subspace of. We can prove that L infinity of E is a subspace of the linear space. We already proved that F with this equivalence class is a linear space. So we can prove that L infinity of E is nothing but a subspace, or in particular it is also a linear space. So how can you prove that this space is also a linear space? So for that we want to verify two axioms, that is which is closed under vector addition and which is closed under scalar multiplication. So for that I take two elements, F and G belongs to L infinity of E, which means F and G are measurable functions and essentially bounded. And they are essentially bounded. When they are essentially bounded, we can have two essential bound for F and G, right? Which implies there exists some m greater than 0 and n greater than 0 such that modulus of f of x is less than or equal to m almost everywhere on E by the essential boundness of F, and modulus of g of x will be less than or equal to some n almost everywhere on E. Okay. Now where m can be taken as essential supremum of F on E, and n can be taken as essential supremum of G on E, because if m is not an essential supremum, if m dash is the essential supremum, we can prove that modulus f of x will be less than or equal to m dash, right? So instead of that, I can suppose that this m is the essential supremum. Okay, and this m is the essential supremum and n is the essential supremum of G. Okay. Now we want to prove that their sum is also belongs to L infinity of G. To prove that f plus g belongs to L infinity of E, we need to prove that f plus g is also essentially bounded. That means we have to find out an essential bound for f plus g. Okay. Now for that, consider modulus of f plus g of x. By definition, it is modulus of fx plus gx. Okay. And modulus of fx plus gx will be always less than or equal to mod fx plus mod gx, right? And mod fx is we have less than or equal to m, and mod gx is we have less than or equal to n. So we get f plus g of x is less than or equal to m plus n. So which means which is almost everywhere on E. So this also almost everywhere on E. So which implies m plus n is an essential bound, right? Essential bound for modulus of for f plus g, which implies f plus g is essentially bounded. When a function have an essential bound, that function will be essentially bounded. So the function f plus g is essentially bounded on E. So which implies f plus g must be belongs to L infinity of E. Okay. Now for the second part, we need to prove that it is closed under scalar multiplication. That is, if alpha belongs to R and f belongs to L infinity of E, we want to prove that alpha into f belongs to L infinity of E. Okay, we want alpha into f belongs to L infinity of E. Okay, so for that we need to prove that alpha into f is essentially bounded. Okay, so you consider alpha into f of x modulus, which is equal to mod alpha into f of x, which is equal to mod alpha into mod f of x. Since f is essentially bounded, we have which is less than or equal to mod f of x is less than or equal to m almost everywhere on E. So you can consider mod alpha into m is an essential bound for the function alpha into f, which implies mod alpha into m is an essential bound for alpha into f. So which implies alpha into f is essentially bounded function. Therefore, it is also belongs to L infinity of E. That means L infinity of E is closed under vector addition and scalar multiplication. Therefore, it is a subspace of the linear space F restricted to these equivalents or equivalent classes. That means it is itself a vector space. So we proved that capital LP of E is a vector space for 1 less than or equal to p less than infinity, and capital L infinity of E is also a vector space. Right? So I can write capital LP of E for 1 less than or equal to p less than infinity is a vector space over R. And capital L infinity of E is also a vector space over R. In general, I can write that is LP of E is a vector space over R. Vector space over R for 1 less than or equal to p less than or equal to infinity. These two cases are defined in one single case. Okay. Now, from the definition, it is clear that there is some relation between boundedness and essentially boundedness. You know, a function is said to be bounded. F is bounded means there exists some m greater than 0 such that mod f of x is less than or equal to m for every x in the domain, right? Suppose E. Then and f is said to be essentially bounded means there exists some m greater than 0 such that modulus of f of x is less than or equal to m almost everywhere on E. എല്ലാവിടെയും ബൗണ്ടഡ്നെസ് ഇല്ല, പക്ഷെ ഓൾമോസ്റ്റ് എവരിവർ ഇല്ലാത്തവിടെയുള്ള എലമെൻസുകൾ കൺസിഡർ ചെയ്താൽ അവരുടെ മെഷർ 0 ആണ്. ഓക്കെ, സോ it is clear that every bounded functions are always essentially bounded, right? എല്ലാവിടെയും boundedness ഉണ്ടെങ്കിൽ that is trivially be essentially bounded, right? So which implies every bounded function is essentially bounded. What about the converse? But we can't say every essentially bounded function is bounded, right? But converse need not be true. That means essentially boundedness doesn't imply boundedness. For example, if you consider a function f is a mapping from closed interval 0, 1 to closed interval 0, 1, okay? And we define f of t equal to, it is a piecewise defined function. Since our domain is closed interval 0, 1, what are the elements in closed interval 0, 1? 0 and 1, and elements in between 0 and 1. What are the elements in between 0 and 1? It is 1 by 2, 1 by 3, 1 by 4, etc. So it is of the form 1 by n's and any other elements, right? So I can split these elements such that if t equal to some 1 by n format, 1 by n format there will exist elements some 3 by 4 അതൊക്കെ ഉണ്ടാവില്ലേ ഇവിടെ. അപ്പോൾ അതല്ലാത്ത 1 by n ഫോർമാറ്റിൽ വരുന്ന എലമെൻറ്റ്സ്, if your elements are the form 1 by n, then we take the function value as n, it's reciprocal. Okay, and t itself, identity function itself, if t is not equal to 1 by n or otherwise, not equal to 1 by n means any other points other than the format of 1 by n otherwise. Okay, so it is clear that the function is not bounded. Why? Clearly f is not bounded because in the neighborhood of 0 we have elements are 1, 1 by 2, 1 by 3, 1 by 4, etc. At these numbers function value is n. So when n tends to infinity, 1 by n tends to 0, then n tends to infinity means the function value will goes to infinity, right? So when t equal to 1 by n comma f of t equal to n, and this tends to infinity as n tends to infinity, right? Therefore f is unbounded. But we can prove that this function is essentially bounded because its essential bound is 1. But essential supremum of this function f is equal to 1. Therefore, it is essentially bounded. Okay. Why which is essentially bounded? This function is essentially bounded means we can prove that modulus of f of x is less than or equal to 1 almost everywhere on E. So which are the points the function f which is greater than 1? So you consider set of all x in capital E such that modulus of E means here closed interval 0, 1, okay? Modulus of f of x is greater than 1. Modulus of f of x is greater than 1 means these x are nothing but 1 by n's, n equal to 1, 1 by 2, 1 by 3, etc. So what is the measure of this set? This set is actually denumerable, right? So measure of this set is 0. Okay, since the measure of this set is equal to 0, in all other points the function is clearly less than or equal to 1 because it is only 0 to 1, okay? So the function has the maximum image as 1, right? So the function is clearly essentially bounded but not bounded. Therefore, essentially boundedness doesn't imply boundedness. So what do we have proved? We proved that capital LP of E is a linear space and capital L infinity is also a linear space. Okay.